This is Bob Capetta from the University of Illinois at Chicago, and this lesson is Work Problems in Calculus Springs. We're going to start with our basic definition of work. Work is force times distance. So for a constant force, you just take that constant force and multiply it by the distance traveled to get the work. But we're going to examine variable forces. So we're going to have a function f of x that is going to define the force at every value of x. So if I have a small change in x, the change in work is just that variable force times that small change in x. If we make that change small enough, this will essentially be a constant function. That's how we perceive it, at least. Now, the total work will be the sum of all the change in works. So over a whole bunch of small changes in x, the total work will be the sum of the change in works, the sum of the f of x times change in x. That'll be our total work for some numbers x that are changing, maybe 0 to 5, 1 to 3, whatever that might be. But again, f of x is a variable force. This is for relatively small changes in x. We're going to shrink that change in x to 0. By shrinking that change in x in 0, this sum will become an integral. And we're going to get our formula for work. Work will be the integral over some interval from a to b of the force function f of x dx. So this is what we're going to use to find the force that is done, find the work that is done for a given variable force. So we're going to take a look at spring problems in this lesson. So in essence, we are starting with a spring and either stretching it or compressing it. We want to find the work that's involved. So we have a force of 10 newtons, stretches the spring 0.1 meters from equilibrium. So you imagine a spring is hanging, and if you want to stretch it 1/10 of a meter, we need 10 newtons to do that. Obviously, different springs will behave differently. A slinky is going to have a different spring constant than springs on a car. So we need to find that spring constant, and then we use that to determine the work necessary to stretch a spring, in this case, 0.25 meters from equilibrium. But our first goal is going to be to find the spring constant, and we're going to use Hooke's law to find the spring constant. Hooke's law tells us F equals kx. So our question here gave us what? F, 10 newtons, x, 0.1 meters. So we have F and we have x. So we can go ahead and solve for k. Remember, our Hooke's law tells us F equals kx. So there we go. 10 newtons will equal k times 0.1 meters for this spring that we have in this problem. So divide both sides by 0.1 meters, and I get k is 10 divided by 0.1, 100 newtons divided by meters. So that is our spring constant, and you'll remember that we had our formula for work. What was that? Work is the integral from a to b of f of x dx. Hooke's law tells us f is k times x. Our k is 100, so our function f will be 100x. So make that substitution. Again, there is our integral for work for a variable force. So our work will be an integral of 100x dx, but we have to think about what these endpoints are going to be. So we've identified the spring constant. Now let's take a look at what this question says. How much work is needed to stretch a spring 0.25 meters from equilibrium? Equilibrium is 0. When we stretch, that's considered positive. When we compress, that's considered negative. So we are stretching from equilibrium from 0 to 0.25 meters beyond equilibrium. So work will be from 0 to 0.25 meters. And our function f of x we have over here is 100x dx. And now all we have to do is evaluate that integral. So let's quickly do that. The antiderivative of x is x squared over 2. So we have 100 x squared over 2 evaluated as x ranges from 0 to 0.25. 100 over 2 is, of course, 50. 50x squared as x ranges from 0 to 0.25. Plug in those numbers and subtract. So 50 times 0.25 squared minus 50 times 0 squared will give us an answer. But before I show you the answer, let's think about our units. Remember, our K was newtons per meter. So this 100 was 100 newtons per meter. X is in meters. So newtons per meter times meter just gives me newtons. Change in X, change in distance, is also meters. Newtons per meter times meter gives me Newton meters, which is joules. So my answer is 12.5 when I do the arithmetic. And the units, again, newtons times meters, which is the same as joules. So let's take a look at another question. We have a force of 30 newtons is required to stretch a spring 0.2 meters from equilibrium. So this is a different spring. It will have a different spring constant. The first thing we need to do is to find that spring constant by using Hooke's law. And then we're going to determine how much work is needed to compress a spring 0.4 meters from equilibrium. So we envision this spring hanging. We're going to push it up, compress it 0.4 of a meter from where it's hanging. And then our second question here is how much work is needed to stretch a spring 0.3 meters from equilibrium. But before we do this, I have to appeal to Hooke's law. Remember, Hooke's law is F equals kx. Force used to stretch x units will enable us to solve for k. What are we given here? Our force is 30 newtons. F is 30 newtons. Our x is 0.2 meters. That should enable us to go ahead and solve for the spring constant k. So making that substitution, dividing both sides by 0.2, we get 30 newtons divided by 0.2 meters is k, or 150 newtons divided by meters is k. So that's going to go ahead and give us what? That's going to give us the k that we need. But our force for this spring, big F, is kx. So our variable function for the force will be 150x. F of x, 150x. Now, what are we trying to do here? What was our goal? Let's go back to the question. How much work is needed to compress a spring 0.4 meters from equilibrium? So assuming we're starting at equilibrium, we're starting at 0, and then we're compressing it 0.4 of a meter, pushing it up. So what will my integral be? We need to determine a and b, starting at 0, going to negative 0.4. Seems a little strange because you'll notice that this is essentially backwards, right? Starting at 0, then going to negative 0.4, we're going to the left. But that's acceptable. That'll work for us. So let's go ahead and do that integral. Integral from 0 to negative 0.4 of 150x. Antiderivative 150x squared over 2 from 0 to negative 0.4. That, of course, is 75x squared from 0 to negative 0.4. Plugging in those values and subtracting. 75 times negative 0.4 squared minus 75 times 0 squared gives me what? Gives me 12 newtons times meters, or 12 joules. Again, just to remind you, 150 newtons divided by meters times x meters gives us newtons, times dx meters gives us Newton meters. And we've got one more question for us to do here. Let's take a look at that. How much work is needed to stretch a spring 0.3 meters from equilibrium? So how will this be different? We're starting at equilibrium, we're starting at 0, and we are stretching 0.3. So our integral will go from 0 to 0.3. Now it's the same spring. So the spring constant we used in the previous problem, we can also use in this one. So our spring constant was 150. So our work will be the integral from 0 to 0.3 of 150x dx. F of x is 150x. Dx, integral of the spring constant k times x dx is what's going to work. Integral of f of x dx will give us the work. So while evaluating this integral, of course, 150x, antiderivative 150x squared over 2, as x goes from 0 to 0.3. 150 over 2, again, is 75. So we have work is 75x squared, as x ranges from 0 to 0.3. Plugging in those values, 75 times 0.3 squared minus 75 times 0 squared will give us an answer of 6.75 Newton meters, or 6.75 joules. And that will conclude this lesson.